Hello, and welcome to our review session today. I'm Michelle Krummel, and I'm going to be working through solutions to a practice exam with you. You can download the practice exam using the link in the description below. So let's get started. For this first problem, we have a table to work with, and we're told that the twice differentiable functions f and g are defined for all real numbers x. So it's important to note what this means when it says twice differentiable functions f and g for all real numbers x. Twice differentiable means that the second derivative exists. The first derivative exists and the second derivative exists, and here it's telling us that they exist for all real numbers x. So we know that our function f is differentiable, and we know that our function f prime is differentiable. Okay, we're also told values of f, f prime, g, and g prime for selected values of x are given in the table above. The first part of this question asks us to find the x-coordinate for each relative minimum and relative maximum of f on the closed interval from -1 to 8, or to explain why there are no such values. So what are we looking for if we're hoping to find a relative minimum? So relative minimum is going to occur when the derivative of that function, and we do want to be really careful about naming our functions. We have so many functions, even just on the screen right now, that we're working with. We need to be really clear when we refer to a function, which one we're referring to. So let me do a better job of that and say that f has a relative minimum when f prime equals 0 and is changing from negative to positive. We know that's what we're looking for at a relative minimum. So we want f prime to change from negative to positive. Negative to positive. And then for our relative maximum, similarly, we are looking for f prime to change from positive to negative. So let's go to the table and see if we can identify points where that is happening. All right, so f prime is this row in the table. And are there any places where the f prime values are changing from negative to positive? Now, the table might look a little bit strange to you because it has some numbers in it, it's got some of these words in it, but we want to pay attention to these x values. So here x equals -1 and here x equals 0. And in between that, this description is for all the x values, not including 1, not including 0, but all the values strictly in between -1 and 0. So we know that x is positive everywhere in between -1 and 0. And then we can see at 0, something is changing, because now after 0, until we hit x equals 2, all of those f prime values are negative. So f prime did change sign at x equals 0, right here at x equals 0. But it didn't change from negative to positive. So that's not a relative minimum, that's a relative maximum. So x equals 0 is going to be a relative max. So still looking, is there anywhere where f prime changes from negative to positive? Well, it's negative all the way until we hit 2. And then it continues to be negative after that on the next subinterval until we hit 4. And then it continues to be negative after that until we hit x equals 8. So we don't have a relative minimum for the graph of f. We do have a relative maximum, however. So we're going to write where we have a relative maximum, and we're going to explain how we know that it's a relative max. And we also want to pay attention to the fact that the question asked us to find the x-coordinate. So we want to make sure we give that as part of our answer. And again, make sure you're naming your function. So we'll say f has a relative maximum at x equals 0, since f prime changes from positive to negative. And it changes from positive to negative specifically at x equals 0. Okay, so that would be a complete response with justification. For the next part of this problem, we're told that h is a strictly decreasing and twice differentiable function such that h prime of 2 equals f prime of 2 and h prime of 8 equals f prime of 8. Then we're asked to evaluate this definite integral of h double prime of 2x over h prime of 2x dx. So in order to integrate this, we're going to use u substitution. So you have to make a choice. What are you going to let u equal? And we've got a couple of options here. Typically, when you have a quotient, you're going to want to choose something in the denominator to be your u. Now, that's not always true, but oftentimes that's true. So in this case, we are going to let u equal h prime of 2x. And that gives us an equation that relates u and h prime. Now we need an equation that relates dx and du. So we're going to take the derivative of both sides here with respect to x. The derivative of u with respect to x is du dx. And the derivative of h prime of 2x with respect to x is h double prime of 2x times 2. And we can rearrange our terms here a little bit. I'm going to divide both sides by 2, and I'm going to multiply both sides by the dx. So I'll have 1/2 du equals h double prime of 2x dx. And the reason I chose to do that was because I see that I have h double prime of 2x dx in my integrand, and I have h double prime 2x dx here, so I can make a direct substitution. I can replace what I've highlighted in yellow with 1/2 du. So let's go ahead and make our substitutions. So I've got the integral. I'm replacing h double prime 2x dx with 1/2 du over, and then I'm replacing h prime of 2x with u. And this is a definite integral, but I'm not going to use 1 and 4 for my lower and upper limits of integration here because those are x values. In our dx problem, those represent x values. And in this new integral, we want everything to be in terms of u. So we have an option of converting our bounds in terms of u, or we can wait until the end when we get the u back out of the problem and then use the original 1 and 4. Let's go ahead and convert our bounds. So in order to do that, I'm using this equation that relates the u and the h prime. And I'm just going to start with this x equals 1. So when x equals 1, just going to write at x equals 1. Let's substitute 1 in for x. We get u equals h prime of 2. And we're told that h prime of 2 is equal to f prime of 2. F prime of 2 equals -1. So u equals -1. So instead of a lower bound of x equals 1, we can use a lower bound of u equals -1. And then let's convert that upper limit of integration. When x equals 4, I'm going to substitute 4 in for x. I get u equals h prime of 8. U equals h prime of 8. And we're told that h prime of 8 equals f prime of 8, and we can get that value from the table. That is -6. -6. So we have the upper limit of integration, u equals -6. I'm going to rewrite this integral, clean it up a little bit. It's the integral from -1 to -6. The 1/2 is a constant multiple, so I can bring that outside of my integral. And then du over u I can write as 1 over u du. And that is one that I recognize. The integral of 1 over u du is the natural log of the absolute value of u. So this is going to equal 1/2 times natural log absolute value of u from -1 to -6. Then we're going to sub in our upper bounds. So 1/2 times ln, the absolute value of -6 is 6, minus ln, and the absolute value of -1 is +1. The natural log of 1 is 0, so this gives us an answer of 1/2 ln 6. The next part of this question asks us to use a right Riemann sum with 4 subintervals to estimate the integral of f dx on the interval from -1 to 8. So let's highlight some important parts of the instructions here. A right Riemann sum. We want to make sure that we do use the right y value at each of our endpoints for our subintervals. 4 subintervals. We want to make sure that we are using 4. And then estimate is another keyword here. The answer that we get, that we're computing with our Riemann sum, is only an approximation for the value of the integral. So we need to be careful with our notation and not say that it is equal to the integral. Let's go ahead and set up our subintervals. We need 4 of them that go from -1 to 8. So we'll go from -1 to 0, from 0 to 2, from 2 to 4, and then from 4 to 8. That gives us our 4 subintervals. What I like to do next is find the width of each interval. So from -1 to 0, that has a width of 1. From 0 to 2 is a width of 2. From 2 to 4 is a width of 2. And then from 4 to 8 is a width of 4. So those are the widths of our subintervals, or also we can say the width of our rectangles in our Riemann sum. Now we need to get the height of each rectangle, and the rule we're using to find the height of the rectangle is the right end of the interval. So we're using the right value. So this first rectangle, if we can imagine, goes from -1 to 0, and at the right end point of that interval, the function value for f is this 5 right here. So we're using that as the height. I'm going to write it on the right side of my little rectangle. For the next subinterval, the right end point is this 3. So I'm going to put a 3 there. For the next subinterval, the right end point is 0. And for the last subinterval, the right end point is -2. And it is okay that we have a negative value there. That just means that if we were to graph our rectangles, that rectangle would actually be below the x-axis. That's why it has a negative area to it. So you definitely want to show your setup for how you compute your sum. There's often points awarded just for setting it up correctly and showing that you are using the appropriate Riemann sum. So our calculation would be the 1 times the 5, right? The width of the interval times the height of the rectangle. So plus 2 times the 3 plus 2 times the 0 plus 4 times the -2. And that answer is numeric. You do not have to simplify it. You can leave it just like that and move on to the next part. And because this is a timed test, I would encourage you to do that. If you do take the extra time to write down that this is our approximation for -1 to 8, f of x dx, you want to make sure you're not using an equal sign there. Use your approximation symbol. And if you did want to simplify that, 5 plus 6 plus 0 minus 8 is equal to 3, right? 11 minus 8, 3. So 3 would be our approximation for the integral. The next part of this equation is asking us to evaluate a limit. The limit as x approaches 2 of g of x cubed over e cubed minus e to the power f of x. Evaluate the limit means find the value of the limit. So we're going to work through this until we find out what this limit is equal to. And when you first approach a limit problem, you should try direct substitution. Try substituting 2 in for x. If you get a real number, then that's your answer, that's your limit. So let's see what happens when we let x equal to. G of 2 cubed would be g, and g of 8 is equal to, let's see, g of 8, you can read from the table, is equal to 0. In the denominator, e cubed minus e to the f of 2 equals, well, f of 2, we can read from the table, that's 3. So e cubed minus e cubed, that is also 0. So when your numerator is approaching 0 and your denominator is approaching 0, we have this indeterminate form. And this is one of the indeterminate forms that will allow us to use L'Hopital's rule to evaluate this limit. So I've sort of informally determined that I can use L'Hopital's rule. My notation isn't very good here, so I'm going to erase what I have and write it out properly. Now that I know that I need to use L'Hopital's rule, I want to make sure that I'm showing the conditions properly. So to do that, you take the limit of the numerator. You're actually going to write limit as x approaches 2, g of x cubed. Just take the limit of the numerator and show what you get. So we already figured out that this was equal to 0. Then you take the limit of the denominator. We're doing this separately. Take the limit of your denominator. And we also already found that that was equal to 0. So when the limit of your numerator is 0 and the limit of your denominator is 0, you may apply L'Hopital's rule. So I could say next, therefore, L'Hopital's rule may be used. You do not have to name the rule. You don't have to write, I'm going to use L'Hopital's rule. You can just go ahead and use it now that you have checked the conditions for it. But this is a really important step. Don't skip over this step. Oftentimes there is a point awarded for just checking these conditions. So now we can use L'Hopital's rule, and L'Hopital's rule tells us that the limit of the original quotient will equal the limit of the derivative of the numerator over the derivative of the denominator. So we don't want to drop the limit notation yet. This is equal to the limit as x approaches 2 of the derivative of the top. So this requires chain rule, is g of stuff. So derivative of g of stuff, g prime of stuff, times the derivative of the stuff over. And in the denominator, we're taking the derivative of e cubed minus e to the f of x. E cubed is a constant, so the derivative of that term is 0, minus e to the power f of x. This also requires chain rule. This is e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So e to the stuff, don't change that inside function there. That's e to the stuff. Keep the stuff the same. Now times the derivative of the stuff. So f prime of x. And we're going to evaluate this limit using substitution. And if we get another indeterminate form, 0 on the top, 0 on the bottom, or plus or minus infinity on the top, plus or minus infinity on the bottom, then we may be able to use L'Hopital's rule again. So let's just try substituting in the 2 for the x and see what happens. We'll have 3 times 2 squared, so 3 times 4, times g prime of 2 cubed, so g prime of 8, over negative f prime of 2 times e to the power f of 2. And we can find those values using our table. So the 3 times 4 is 12. G prime of 8 is negative 3. 12 times negative 3 on top. So right away I know I'm not going to get this indeterminate form. So hopefully the denominator is also going to give me a real number, and then I will have my limit. Negative f prime of 2. F prime of 2 is negative 1. So negative 1 times e to the f of 2. F of 2 from the table is 3 e cubed, positive 1 times e cubed. All right, so you can leave your answer like that. That is a numeric answer. And again, I would encourage you to do that. Or we could simplify and get negative 36 over e cubed. Negative 36 over e cubed as our limit. For the next part of this question, is there guaranteed a value c on the open interval between negative 1 and 8 such that f double prime of c equals 0? Explain. Anytime you see these questions that say, is there guaranteed a value such that, it's probably referring to one of the existence theorems. So we have 4 existence theorems that we work with this year: the intermediate value theorem, the extreme value theorem, the mean value theorem, and Rolle's theorem. So let's see which one of these theorems seems like it matches the conclusion we're trying to make. The conclusion we're trying to make is that f double prime of c equals 0. Well, none of those theorems specifically say something about the second derivative. So that's one thing that we have to kind of stop and think about. And also, we don't have any information about f double prime in our table. So that's another thing to maybe stop and think about. So maybe we should be thinking of f double prime of c as the derivative of, I have to be careful, I guess, how I write this, the derivative of f prime at c. Is there somewhere where the derivative of f prime equals 0? And that does sound like one of our theorems. Rolle's theorem guarantees that somewhere the derivative of a function will equal 0 as long as certain conditions are met. And again, I said the function there, so I need to clarify which functions I'm referring to. But Rolle's theorem has 3 conditions. If we're trying to show that the derivative of a function, and in this case, the function I'm talking about is f prime. If we're trying to show that the derivative of f prime is equal to 0, we need to verify that f prime is continuous on the closed interval, differentiable on the open interval, and that somewhere in that interval, we have 2 y values that are the same. 2 y values for f prime that are the same. Those are the conditions for Rolle's theorem. And if those 3 conditions are true, then we can conclude that the derivative of f prime will equal 0 somewhere in our interval. So let's look at the row in the table involving the f prime and see if we've got those conditions met. So the first condition, we need f prime to be continuous on the closed interval from -1 to 8. Is that true? Well, remember we were told that f is twice differentiable. So that means that f is differentiable and f prime is differentiable. And that's one of the conditions we're trying to check. Is f prime differentiable? Yes. Where is it differentiable? Well, it's differentiable for all real numbers x. So if it's differentiable for all x, then certainly it's differentiable on the closed interval from -1 to 8. So that condition is met. Let's go ahead and write that one down. And again, we have to name our functions so it's clear what we're talking about. F prime is continuous Oh, I guess that's not what I just said. What I just said was that f prime was differentiable, which is also one of the conditions that we need. So f prime is differentiable for all x, therefore it is differentiable from -1 to 8. And if it's differentiable, that automatically means that it's continuous. We can immediately make that conclusion. If we know that a function is differentiable, then we know that that same function is continuous. Okay, so both of those conditions we know are met just from the fact that we're told that f is twice differentiable. So f prime is continuous, and let me change this and say, and differentiable. On the closed interval. And you can use this type of notation here. If you want closed interval, you're going to include the equal sign under the inequality symbol, or you can use interval notation, which is what I'm more used to using. Closed interval, we would put the square brackets. Now, it is required for f prime to be continuous on the closed interval. It is not required for f prime to be differentiable on the closed interval. It's only required for it to be differentiable on the open interval. In this case, it does happen to be differentiable at the endpoint, so we can say closed interval and get away with that. In general, be careful there. Unless you know that your function is differentiable at the endpoints, don't say that it's differentiable on the closed interval. But in this case, it is true. So f prime is continuous and differentiable on the closed interval from -1 to 8. And there's a third condition. Remember, we have to have f prime having the same 2 y values somewhere in the interval. So we're going to go to the table and verify that. And indeed, we have right here and right here, f prime is equal to 0. Now, it doesn't have to equal 0. It just has to equal the same value for 2 different values of x within our interval. So that's happening here at x equals 0 and at x equals 4. Okay, so my third condition, I can say, and f prime of 0 equals f prime of 4. Therefore, Rolle's theorem, and you do not need to name the theorem. You can just skip where I'm writing Rolle's theorem. You can just say therefore and state your conclusion. Therefore, Rolle's theorem guarantees. And if you're having any doubts about how to phrase your conclusion properly, so you include everything you need to say and you're using proper notation, oftentimes you can phrase it exactly the way it's presented to you in the problem. Here, we were asked, is there guaranteed a value C? So Rolle's theorem guarantees, and I'm just going to use this word for word, notation for notation, as my conclusion. Rolle's theorem guarantees a value C for -1 less than C less than 8, such that f double prime of C equals 0. So when in doubt, go back to the question prompt and see if the conclusion is stated there for you. Otherwise, you can refer to your notes to make sure that you are writing the conclusion properly. Now, the last part of question number 1 says, let h of x equal f of x over g of x. So they're introducing yet another function. Write an equation for the line tangent to the graph of h at x equals -1. We want to write the equation of a tangent line for the function h at x equals -1. And so when you're asked to find the equation of the tangent line for h at x equals -1, you need two things. You need h of -1 and you need h prime of -1. We need both of those things in order to write the equation of our tangent line. Because h of -1, when we figure out what that's equal to, we're going to know the coordinates for the point of tangency. We already know the x-coordinate is -1, but that's going to give us the y-coordinate for the point of tangency. And then h prime of -1 is going to give us the slope of the tangent line. So we need those two things in order to write our equation for our tangent line. So we'll start by finding h of -1. H of -1, I simply need to substitute -1 into my equation for h of x. So it would be f of -1 over g of -1. And we can read those values from the table. F of -1 is 3. G of -1 is -2. So now my point of tangency is -1 comma -3 over 2. Okay, then we're going to need to find our slope. So h prime of x equals, and then we're taking the derivative of h of x to get h prime of x. And here we need to use the quotient rule. So quotient rule is derivative of the top function times the bottom function minus the top function times the derivative of the bottom function over the bottom function squared. And we're going to substitute -1 in for the x. So we can read those values from our table. F prime of -1 is 1. G of -1 is -2. F of -1 is 3. G prime of -1 is 1. Over G of -1 is -2 squared. -2 squared, like that. Now that answer is numeric. You can leave it like that. However, we need to know that value in order to write the equation of our tangent line. Our tangent line equation is going to look pretty messy if we write our slope like this. So let's go ahead and simplify this. This is -2 minus 3, so -5 over 4. That's the slope of the tangent line. Here, the -3 over 2 is the y-coordinate of our tangent line, and the -1 is the x-coordinate for our point of tangency, not for the tangent line. Okay, so the tangent line equation, point slope form, y minus the y-coordinate, so y minus -3/2 will be y plus 3/2, equals the slope, -5/4, times x minus the x-coordinate. So x minus -1 becomes x plus 1. And we can leave that equation in point slope form. There's no need to simplify that to try and write it in slope intercept form. Problem number 2, we're almost there. Problem number 2 gives us a graph to start with, and we're told a particle is moving along the x-axis and it has velocity v of t feet per second at time t seconds on the interval from 0 to 10, closed interval from 0 to 10. The graph of v of t, shown above, actually shown below, right, consists of 4 line segments and a quarter circle. So between 7 and 10, we can see that that is a quarter of a circle. First part of this question, find the average acceleration of the particle on the interval from 0 to 10 and include units in your answer. So average acceleration, we want to make sure we're using the right formula here, or think about the definition. Average acceleration is the average rate of change of velocity. So it's the change in velocity over the change in time. And to compute that, we're going to use v of 10 minus v of 0 over 10 minus 0. So a common mistake that people make is to think that this equation that I wrote down is average velocity. That's not average velocity. That's average acceleration. It's the change in velocity over the change in time. This is average acceleration. And these values, since we have the velocity graph, we can read right from the graph. V of 10 is equal to 0. V of 0 is equal to 1. And 10 minus 0 is equal to 10. So negative 1 over 10. Negative 1 over 10, we want to include units on our answer. Our velocity is measured in feet per second. So in the numerator, we're subtracting 2 values that have units of feet per second. So the units in the numerator, feet per second. In the denominator, we're subtracting 2 times, and the units then in the denominator are second. So units on average acceleration, feet per second per second. And you can write feet per second, but a lot of people prefer to abbreviate feet per second squared. And there we have our average acceleration on the interval from 0 to 10. The next part of this question asks, at what time t is the particle furthest to the left? And so to answer this question, we want to know the total distance that it has moved to the right, and then the total distance that it has moved to the left. So for this particle, since the velocity starts out positive, we know the particle starts out moving to the right. And if we find this shaded area here, so the area between the velocity curve and the x-axis, then we'll figure out how far between 0 and 3 this particle has moved to the right. And so the area here, 3.5. So it has moved a distance of 3.5 units to the right. And then on the interval between 3 and 6, the particle is moving left. And we know this because the velocity is negative. So if we compute this area, we get 0.5 plus 1, so 1.5. And this is how far the particle has moved to the left. And continuing on, and you may not need to continue on because you might be able to just visually tell what's happening here. But if we do continue on, we could calculate this area here. But the particle is moving to the right on the interval from 6 to 10. So that's not going to influence our answer. If we want to know when was it furthest to the left, well, it starts out at some position. It starts out at some position, and then it moves a distance of 3.5 to the right, and then it turns and moves a distance of 1.5 to the left, and then it turns again and moves some distance, I haven't computed it yet, but some distance to the right. So when was it furthest to the left? Well, that would have been at its initial position. So time t equals 0. At time t equals 0. Find the total distance traveled by the particle on the interval from 0 to 10. Total distance. So we want to remember that we are finding total distance and not the net distance traveled, the total distance. So the particle, we said, starts out moving right. And if we find the accumulated area under that velocity graph from t equals 0 to t equals 3, we get how far it moved to the right during those first 3 seconds. So integrating velocity gives you change in position. Change in position we can also think of as distance. But from 3 to 6, we have to be careful because from 3 to 6, it's moving to the left. And if we were to integrate the velocity from 3 to 6, we would end up with a negative value. And then at t equals 6, the particle starts moving to the right again. If we integrate our velocity, we'll have a positive value there. So for total distance, you want to make sure that you take the absolute value of each one of these distances. So we want the total distance for the time it was moving to the right, and we want the absolute value of the distance when it was moving to the left, and then we just add up all of those absolute values. We don't have an equation to integrate, but we know that we can find the value of the definite integral by finding the area under that velocity curve. And because we have, shapes that we recognize and we have formulas for finding the area of these known shapes, we can get that fairly easily. So from 0 to 3, we find the area that I've shaded there in yellow, the area between the velocity graph and the x-axis. So it's 1, 2, a half, and a half, so 3.5. 3.5 would be the distance traveled on that interval from t equals 0 to t equals 3. And then from t equals 3 to t equals 6, we're going to find that area. So we've got 1/2. And then from 4 to 6, or from 3 to 4, it's 1/2. And from 4 to 6, it's half of a 2x1 rectangle. So it's 1. So this is 1.5 here. And if it were a definite integral, that would be a negative 1.5. But again, because it's total distance, we're using positive area. Now, the area between 6 and 10, so it's kind of a strange looking shape here. If we break this apart and just look at the integral from 6 to 7 first, that's half of a 1/3 rectangle. So that part right there has area 1.5. And then from 7 to 10, we want the area underneath that quarter circle. So if we filled in the quarter circle, we would have a 3x3 rectangle, which would have an area of 9. And from that, we want to take away the area of the quarter circle. So the quarter circle has a radius of 3. That means that the entire circle, right, the area of the whole circle would be 9 pi. So the area of the quarter circle is 9 pi over 4. And the area of the part shaded in yellow then would be 9, which is the 3x3 rectangle, minus the 9 pi over 4. So take away that quarter circle. 9 minus 9 pi over 4. And then our total distance, we just add all of those absolute values together. So 3.5 plus 1.5 plus 1.5 plus 9 minus 9 pi over 4. No need to simplify that. You could if you wanted to, but you can also just leave your answer in this form. All right, and almost there. This is the last part to question number 2. On what intervals is the particle slowing down? Slowing down is another way of asking where is the speed decreasing. So you may see it phrased either way. On what intervals is the speed of the particle decreasing? Now, the speed is very closely related to the velocity. They're not exactly the same thing. We know that this can't possibly be the graph of the speed because the velocity graph has some negative values, and speed does not have negative values. Speed only has positive values. But I can very easily sketch the graph of speed looking at the graph of velocity. So when the velocity is positive, speed and the velocity are equal. So the velocity starts out positive, so the speed graph is going to look just like the velocity graph until we get to t equals 3 seconds. And now, where the velocity is negative, the speed needs to be positive. So we just take the absolute value of the graph, and we do that by reflecting the negative portion of the graph across the x-axis. So on the speed graph, from 3 to 4, we would be coming up like so, and then down like so. And then we're back to having positive velocity. So the speed graph and the velocity graph would look the same throughout the rest of that interval. Okay, so what I have in green here is the graph of the speed. And when you draw your speed graph, it's very easy to see where speed is decreasing. It's just when the graph is going down from left to right. So the speed is decreasing here on this interval from 1 to 3. And then the speed is also decreasing here on this interval from 4 to 6. And then it's decreasing here on this interval from 7 to 10. Now, if you're not used to thinking about the problem this way, that's okay. You don't have to graph the speed in order to answer that question. You can just think about the velocity. So the speed will be decreasing wherever the velocity is positive and decreasing. So that is this portion of the graph here, positive because it's above the x-axis, decreasing because it's going down, and then also over here, positive and decreasing. So those two intervals. But the speed is also decreasing, or the particle is also slowing down when the velocity is negative and increasing. So we have to include that part of the graph as well. And these are the three intervals that we saw before when I had sketched the graph of the speed. So let's write out our answer. And we want to be careful how we write this because we are asked to justify. And the justification for the interval from 4 to 6 is different than the justification for the other two intervals. So I'm going to kind of separate this into two parts and say that the particle is slowing down on, so it's the interval from 1 to 3. It's an open interval. We're not including the endpoints there. If you look at the graph at 1, the velocity is not differentiable at x equals 1. So the acceleration doesn't exist at x equals 1 here. And then here, the velocity is not positive at 3. It's not positive or negative. It's 0. So we're not going to include the endpoints there. So on the intervals 1 to 3, union, the union just joins these two intervals together. And 7 to 10, since v of t is greater than 0 and decreasing. Okay, now for the other part. And on the interval from 4 to 6, since v of t is less than 0 and increasing. Now that's not the only way you can justify that response. Instead of saying that the velocity is positive and decreasing, you could also say the velocity is positive and acceleration is negative. And then for the second part, instead of saying velocity is negative and increasing, you could say velocity is negative and acceleration is positive. So you can also justify it that way. Okay, so we made it through our practice exam. If you're looking for some other good resources for exam prep, right here on YouTube, you can check out my own YouTube channel, Michelle Krummel. I've got lots of calculus videos there and some extra practice for the exam. You can look at the videos that we have posted on Marco Learning. So we did a session last week and we've got this one and we have another one coming up on next Saturday. And you can also check out the Advanced Placement YouTube channel where they have their AP live review videos and lots of handouts with extra practice problems for you as well. Thank you for joining us tonight. Good luck, and I will see you next time.